Hello everyone, my name is Nate Robinson and welcome to this presentation on Multibeam Echo Sounders. Before we get into the Echo Sounder itself, just to give you a quick understanding of the vessel that it is being deployed on here at the Marine Field Station, that is the RV Petrel, that is our survey platform. Highlighted with the red arrows, we have our EdgeTech 6205 sonar head, which is pole mounted there on the starboard side. Up on the hard top, we have our two survey grade GPS antennas, which we will discuss a little further. And then inside the cabin is our survey station with our acquisition computer and software and monitors. Here is Steve Everett with just a brief explanation of the multi-beam sonar and the system on board the RV Petrel.
Here, this is a multi-beam sonar, and as the name implies, it's using multiple beams to collect very similar data. This particular one actually does side scan and multi-beam at the same time, but some can just be multi-beam sonar. And the difference in the side scan and the multi-beam systems is the multi-beam sonars will give you 3D or essentially point cloud data from operating on the same acoustic principle, but just with a different scanning frequency and beams. It's going to give you that 3D point cloud data that a side scan is really just giving you one picture in time. What this will also do by giving you that 3D data is tell you the depth. So both of the systems are going to be scanning off to the side of the boat, anywhere from 10 meters to either side of the boat, right? As the boat moves forward, 10 meters each way to, in some cases, 150 or even more, depending on the system. As it does that, a multi-beam sonar is also going to tell you the depth of that water. So I'll show you an example of that when we get inside. So the other operational difference between the systems is this can be run with a pretty simple GPS, but remember it's towed behind the boat, so you don't know exactly where it is. So the position data for a side scan is not as precise as it is with a multi-beam. So if position and size and the 3D structure of like an underwater structure like a bridge is especially important, the multi-beam would be the better tool. The multi-beam is fixed to the boat and utilizes a survey grade GPS. On top of the boat we have two antennas. So there's one, this is a primary antenna, it's getting a position, and then there's a second antenna at a certain separation, a measured separation, that's giving us a more accurate position and more accurate heading data, and all that's necessary to get the 3D point cloud data that we can get out of a multi-beam system. What's also necessary with a multi-beam system that's not when you're just getting side scan images is to take out the roll of the boat, the motion of the boat. So as we sit here in the boat right now, the boat's doing obviously a little bit of this. It's rolling, it's got pitch forward, and it's got yaw. So as you move, this sonar, the multi-beam sonar, is rigid to the boat, so it's moving as well. In order to get that, to resolve that data at a distance from the boat, we need to remove the motion from the data set. And we do that with a motion reference unit. So as we walk in here, mount it about in the center of gravity of the boat, wherever you can get it that makes sense, but as low and as centered to the boat as possible, is a motion reference unit. So it's a high quality positioning, or not positioning system, but a high quality motion sensor that is telling us exactly what's happening as far as pitch, roll, and yaw as the boat moves forward. And the acquisition software that we use is going to take all that into account. So that's way more than you need to know for right now, but you do need to realize that a side scan sonar position is relatively accurate, reasonably accurate. It's going to give you acoustic images of what you see on the sea floor, A multi-beam system is going to give you 3D point cloud data of those structures. It's going to give you depth information across the swath of data. And in order to do that, it's a more sophisticated system. It requires the survey grade GPS system with the 2 antennas and the motion reference unit.
So just to highlight and build upon what Steve was saying, the multi-beam sonar provides water depth. It's bathymetry, and that is done through a point cloud through 3D data. We'll give you an example of that in a little bit. Multi-beam operations, they require the GPS, like we talked about, the two antenna GPS systems that give us RTK, fixed, extremely accurate GPS, and it requires CTD data, which is your sound velocity. They require the motion reference unit and fixed mounting on the side of the boat. Here we have an example of multi-beam on the left and side scan on the right. Both those waterfalls are being played simultaneously. The multi-beam swath kind of changes its range due to the fact that it is a function of water depth, whereas the side scan has an established range or an established swath and collects out to that the entire time. So we mentioned point cloud data. This is just a quick presentation of point cloud. Here we've taken just a cross-sectional sliver of data from a matrix, and as we zoom in, you can see individual points along the beam line, and each one of those points has an X, a Y, and a Z, Z being our water depth. So that's where the multi-beam differs from the side scan. Side scan cannot give you depth for a target, where multi-beam can give you depth for each one of those points, as well as latitude and longitude. Position accuracy is extremely important, because if we sit and try to assign depth, assign position for each one of those points, we need to be accurate, because charts, maps are going to be built from this bathymetry data. So we use real-time kinematics for enhanced accuracy. For our system, we use a paid subscription to a website which sends their GPS corrections from a known surveyed base station. We then apply those offsets into the system, and we can then, knowing where the sonar head is in relation to the antennas, we can triangulate for each one of those 3D points. The motion affects accuracy, and so we have an MRU, a motion reference unit, to compensate for that. And then conductivity, temperature, and depth. Those are all key features that affect sound velocity, affect the water density. So as the water density changes, your sound velocity is going to change. It's going to speed up, it's going to slow down, and that affects position as well. So we take casts for our system in a tidal system. We take casts about every hour to get new sound velocity data and apply that to our survey. Our position accuracy, it's great that we have accurate position, and we then also have accurate depth. But what are we applying that depth to? We are referencing it to. We say that it is 5 feet. 5 feet to what? 5 feet above this, 5 feet below that. And so we use things called datums. The datum here in red, the North America vertical datum, is a pretty standard used datum across the survey community here in the United States, and we can reference to that. We typically then will reference down to mean, lower, low water. A datum is just a point of reference at which you are saying it is 5 feet below or above a point of reference, a datum. So we collect multi-beam data, and it is this beautiful painted color picture, but yet it's not the finished product. We still need to post-process. This image here is unprocessed data, and it's kind of rough. The depth contour colors are just not crisp. They're kind of clunky, so to speak. So to post-process, we can look for erroneous data points here in this 3D cloud view that we looked at earlier. As I spin it around, I'm looking for data points that just don't seem to make sense with the rest of the surrounding area. And I noticed that there are some of these red points up above the cloud there that stand out. They could be fish, they could be air bubbles in the water, but they will affect our final products. So I want to go ahead and cut them out of there. And so I can go through a survey, through a matrix, and look at the 3D cloud for each cross section, or I can do it in different views, which the next slide I will show you the profile view of a survey. So here we have a cross section of the river. Each one of these colored lines is just color-coded survey lines that we drove, so individual survey lines. And we can see that at the edges of the range, so for each line, at the extremes of the range, the data gets noisy and stretched out, and it's just not accurate point data. So we want to go ahead and we want to cut that kind of data out, clip that out, and that will help smooth up our image. Here we've clipped out those noisy data points at the end of the ranges for each of the survey lines, and that will then allow us to produce nice final products as we scroll through, and we do this to all of the profile views, the cross-sectional views. Produce nice, smooth final products. This is on the left is Chestnut Neck stretch of the Mullica River there by the Garden State Parkway Bridge, and then that is Blood Ditch there on the right with nice, beautiful colors of depth contour. Here we have the Blood Ditch area, and we've created a tin model, and we can spin that around. We can go ahead and give it some three-dimensional depth and really get to see what a multi-beam can produce. It produces the seafloor, stuff that we don't see as we're driving the boat, but the multi-beam can create these images for us. Your reds are going to be your shallower areas, and we get down to the blues, those are going to be your deeper areas. So we see some, those are actually little strips of marsh or islands there at the cuts, and then we have a little further back we have a nice ridge, just a beautiful bathymetric image of the seafloor. Multi-beams, they can be applied to biology as well. We can take the backscatter of the sonar signal. Now the backscatter isn't the sonar signal itself. It's not the speed of the sound wave, which is what we get when we get depth. The backscatter is the intensity of the sound wave's return, because energy is going to be lost. So it's sent out from the transducer. Well, some of that energy is going to be lost and absorbed or deflected by a target. So when that energy is returned, it is not in the same value that it left. So we can calculate the intensities of those returns and use what is called backscatter to create maps. This is habitat mapping using backscatter, so we can delineate seafloor habitat, shell, sand, silt, mud, those sorts of things. And then here is more recent applications of the multi-beam is collecting the water column data. That candy cane stripe there on the top left of the left image, that would be the line that the sonar would have traveled, and this is just a sliver of water column data. And in that water column, you will see fish, you will see gas plumes if you were going over vents, and then on the right is another example of that water column data highlighting a school of fish in red. So the multi-beam sonar, in summary, it is used for underwater mapping, and it creates bathymetric charts, depth charts. It's used for habitat classification utilizing the backscatter data, and sediment distribution maps as well using backscatter data. And just like the side scan, it can map large areas of the seafloor in one pass or in several passes, as compared to using a drone, an ROV or a diver. Restrictions, just like with the side scan, there is cost involved, and these systems are a little more complex. You have to have the motion reference unit. You have to have the survey grade GPS with the higher accuracy. Multi-beams are a little bit more water dependent. Very shallow multi-beam surveys can be difficult. But alternatives to the multi-beam, if we wanted to do a habitat map, or with the multi-beam we use the backscatter. If we didn't have a multi-beam, we would have to go out and take individual benthic grabs and then kind of interpolate in between the grabs and create our maps that way. But they can't cover large areas doing it like that. It's time intensive, and your data density is extremely less.